Our topic for today is about exact equations. Suppose that we have this differential equation of the form m dx plus n dy equal to 0. So first order differential equation. If the coefficient m, n, and the partial derivative of m with respect to y, and the partial derivative of this coefficient n with respect to x are continuous functions of x and y, then the differential equation m dx plus n dy equal to 0 is an exact equation, okay, provided that this is satisfied. So this equation is satisfied. The partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x for us to be able to conclude or say that this differential equation here of this form is an exact equation. Okay, so firstly, we are going to analyze the test for exactness. How can we be able to determine the exactness of an equation? So suppose that we have this function f of xy that can be found that has its differential df equal to m dx plus n dy. Taking the solution of this differential, total differential, will give us f of xy equal to c. So what is the process? We integrate. So basically will give us the solution of the differential equation. So again, this function is a function of x and y. If we are to differentiate these functions, it will give us, or this equation, df is equal to 0. Thus, this equation can be written as m dx plus n dy equal to, what is df? So we have 0. So we can be able to put into this form the resulting differential, total differential of the given function here. From calculus, the total differential of the given function, which is m dx plus n dy, can be written as the partial derivative of the function with respect to x, since the first term contains the differential of x. So we know that m is an expression containing x and y, and n is an expression or a function that contains the variables x and y. And we can equate that here. M is equal to partial derivative of the function with respect to x, and n is equal to the partial derivative of the function with respect to y. Now what we will do now here is, from these equations, we will take the derivative or the differential with respect to, since m is the coefficient of dx, we are now to differentiate this equation with respect to y for exactness. And then for this part right here, since n is the coefficient of dy and it's equal to the partial derivative of the function with respect to y, we will now differentiate this with respect to the variable x. So this is the result of taking the partial derivatives of the given functions, since it involves two independent variables. So taking the partial derivative of m with respect to y, it will give us, going back here, so this is first derivative, right? So if you take the derivative of this, it will give us second derivative. It will result to second derivative of the function, however, with respect to y. So just copy partial of x here. And the same with n here. So taking the partial derivative of n with respect to x will give us, so this becomes second partial derivative of f with respect to x and y. So in calculus, we can equate these expressions here, or this partial derivative. So partial derivative of f, second partial derivative of the given function with respect to y and x is equal to the second partial derivative of the function with respect to x and y. So having said that, Therefore, the given equation of the form m dx plus n dy equal to 0 is an exact equation, provided that the condition that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So that's basically what we need for us to be able to determine if the equation is an exact differential equation. So first, you are going to test the given differential equation of this form. If the given dE satisfies this test for exactness, then it is an exact differential equation. Okay, so we'll now go to solving exact differential equation. There are actually two methods that we can use in order to solve an exact differential equation. So we start first with the long method. And here are the steps. Okay, so we will let f, of course, the given solution of a dE is f, yeah, the function of f is equal to c. But in here, we have written the symbol phi. So this is actually brought about by the partial derivative. So we can actually put as part of our solution. So f plus phi equal to c be the solution of an exact dE of the form m dx plus n dy equal to 0. Okay, this is an exact differential equation. So we let this as the solution of this exact dE. So first is we set what coefficient to use. Okay, take note that the coefficient is equivalent to partial derivatives of the function. Okay, so you may set the partial derivative of the function with respect to x or the partial derivative of the function with respect to y equal to n as your starting equation. Okay, so here in these steps, I will be selecting this. I'll be setting this equation. So m is equal to the partial derivative of f with respect to x. Okay, so we arrange this equation into this format. So as you can see, I have written this part right here as total differential df equal to m dx. Okay, so we will integrate this equation. So basically, you copy what this function represents. So you copy here, you plug in here, and then you integrate both sides. So you have the given function equal to the integral of m dx. Plus, of course, you have the arbitrary constant c, right? If you integrate, so you put plus c. But in this case, we will be using this symbol of the function. So phi of y. So it means that when we integrate this part right here, we are to integrate with respect to x. It means that since this function contains the variables x and y is held constant. Okay, take note of that. Now, after determining the solution of this given equation, you will now differentiate this function here, this equation with respect to y. So we'll differentiate that. Then we equate. So first is we set, we integrate, and then we differentiate. Since we know that this partial of f with respect to y is equal to n in our previous derivation of the testing for exactness, we equate that to n. That's the next step. So SIDE, side, set, integrate, differentiate, and then equate. And then after equating to n, it will give us actually, it will restore to an equation phi prime of y equal to a pure function of y. So the next step will be to integrate. So you know that phi prime of y is equal to d phi over dy. You separate the variables there, and then this part of our solution will give us the value of phi. And then after that, we will substitute the value of phi on the given solution here. Now let's review again the steps of the long method or the side is method, for you will be using this in solving your problem set posted in the course site. I'll also show you another method that you can use to check your solution. First order differential equation of the form m dx plus n dy equal to 0 is said to be exact equation if it satisfies this condition that the partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x. Okay, let's call the first method as a long method. Okay, so we have an acronym for this side is to remember that an exact equation m dx plus m dy equal to 0, where m is equal to the partial derivative of the function with respect to x, and n is the partial derivative of the function of both x and y with respect to y. So this is actually presented in the derivation for the test for exactness. So sidis means you set, so you choose from one of these. So you may set partial of f with respect to x as your starting equation. So you may set partial of f with respect to x, which is m, as your first equation, and that df equal to m dx. In this case, since m is not a pure function of x, so when you integrate this given term, the variable y is held constant. Okay, so after you have set, then you integrate both sides, and then you will determine the solution, which is f equal to the answer to this, m dx, plus the constant of integration. In this case, the variable y is held constant. Okay, and after you integrate, so you differentiate this. Okay, differentiate the function with respect to y. Okay, let me just rewrite this. So partial of f with respect to y. So now we differentiate this with respect to y, taking note that x is held constant, and we know that in our derivation, this is equal to n. So this is the time that we equate. Okay, this is the equate step to n. And equating the resulting derivative will give us phi prime of y. So in this case, we are going to integrate. Okay, equate, integrate this d phi equal to f of y dy. And we will determine the value of phi, which is a function of y. And the solution, f is equal to, or f plus phi equal to c, is a solution to our differential equation, which is exact equation. So we will be clarified by these steps later once we have started solving a first order DE. Now method 2, so we call method 2 as the short method. So why short method? Because we'll no longer be utilizing several steps in solving the exact DE. So we call it the short method. So what you will do is, first, we have a first order DE, exact DE, m dx plus n dy equal to 0. What we will do is we integrate the first term, integral of m dx. In this case, you have to take note that y is held constant. And then you integrate the second term, n dy. So you integrate only those terms, okay, with pure function of y. So if you see x, you eliminate that entire, or that term containing x again. So integrate only those terms without x, okay, equal to the arbitrary constant c. So that's the short method, or the second method. Example number 1. Solve 3x times the quantity xy minus 2 dx plus the quantity x cubed plus 2y times dy equal to 0. So let's test this dE for exactness. So we have m equal to, we distribute 3x into this function. So we have 3x squared y, 3x times minus 2. So you have minus 6x. So we take the partial derivative of m with respect to y. So it means that when you differentiate, the variable x is held constant. So we copy 3x squared and then differentiate y with respect to y, so times 1. And then the second term is a function of x held constant. So if you differentiate this, it will give us 0. Okay, now we have n equal to x cubed plus 2y. Now we take the partial derivative of n with respect to x. So in this case, y is held constant. So the first term is a function of x, so we will differentiate this. It will give us 3x squared, and then differentiate the constant, so that's 0. So as you can see, the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. That's why this dE is an exact differential equation. Now we are going to solve this dE in 2 different methods. So let's start by solving using the long method. Okay, so remember the side is acronym that we have. So, okay, so the first step is you set. So we will set this one to be our starting equation. So you know that m is equal to partial of f with respect to x. So we have partial of f with respect to x equal to 3x times xy minus 2. We have 3x squared y minus 6x. And then we rewrite this equation into total differential form, taking note that y is held constant. So 3x squared y minus 6x times dx. And our constant of integration is y. So set, then we integrate both sides of the equation. So we have f equal to, so first term 3x squared y dx, y is held constant, so you just copy 3y, and then you integrate x squared dx. It will give us x cubed over 3. For the second term, a pure function of x, so minus 6x dx, we'll integrate that. It will give us 6x squared over 2. And then you copy the constant of integration, phi of y. Now we will arrange this first, simplify before we proceed to the next step, which is to differentiate. Okay, so cancel 3. You have x cubed y. 6 divided by 2 is 3. So you have minus 3x squared plus phi of y. Now this will be our solution if we have the value of phi. Okay, and then equate that to the arbitrary constant c. Okay, let me erase this first, and let's proceed to the next step, which is to differentiate. Okay, so we will differentiate this function with respect to y. Means that x is held constant. So we copy x cubed and then differentiate y. So with respect to y, so times 1. Function of x, if we differentiate this, since x is held constant, the result is 0. And then phi of y is a function of y, so we will differentiate this. It will give us first derivative of phi with respect to y. Okay, now the next step is we equate. Since partial of f with respect to y is equal to n, so we equate this resulting derivative to n. Okay, this is our n. So it's x cubed plus 2y. And this part, we can be able to cancel um, x cubed, giving us a pure function of y. We know that phi prime of y is d phi over dy. Okay, and we have 2y here. And then we cross multiply, giving us d phi equal to 2y dy. We now proceed to the next step, which is to integrate. So integrate both sides of the equation. It will give us the value of phi, which is 2y squared over 2. We cancel 2. Now the value of phi, which is a function of y, is y squared. Now for our solution, since we already determined the value of phi, which is y squared, therefore the solution to our differential equation is this one. It's x cubed y minus 3 x squared. The value of phi is y squared equal to c. So this is our solution. So we are done. So the last step is actually substitute. So we did substitute to our solution, which is f plus phi equal to c. Okay, now we are going to solve this DE again using the short method. Now, using the first or the second method, okay, where you integrate each term. So integrate m dx. Take note that y is held constant, and then you integrate the second term in dy. But in this case, you integrate only those terms without x, okay, and then equate to c. So here you have the integral of distribute this 3x. So you have 3x squared y minus 6x times dx. And for this one, so without x, it means that the first term here will be eliminated. Second term is a pure function of y, so just integrate that. So 2y dy equal to c. So integrate the first term with respect to x. Y is held constant, so we have 3x cubed over 3. Okay, just copy y. Because y is held constant here, you have 6x squared over 2. And here you have uh, plus 2y squared over 2 equal to c. If you simplify, so you have y squared, you have 3x squared minus 3x squared, and you have x cubed y. So you have the same answer. Okay, our next example is solve the quantity 2x cubed minus xy squared minus 2y plus 3 times dx minus the quantity x squared y plus 2x times dy equal to 0. The first step is to test this dE for exactness. So our m here is equal to 2x cubed minus xy squared minus 2y plus 3. So we take the partial derivative of m with respect to y. So it means variable x is held constant. So first term is held constant, and then second term you have minus x, and then differentiate y squared, so you have 2y, and then third term that's minus 2. The last term is a constant, so that's 0. So the partial derivative is equal to minus 2xy minus 2. Now we go to n. So we include the minus sign here. So we distribute the negative sign. So we have negative x squared y minus 2x. Now we take the partial derivative of n with respect to x. So here y is held constant. So we copy minus y and then differentiate x squared, that is 2x. Second term is a function of x, so we can differentiate this minus 2. So the result is minus 2xy minus 2. So as you can see, the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Therefore, this differential equation is an exact equation. Okay, so we are going to solve this first order DE, exact differential equation for that matter, in two ways. Okay, the first one is using the long method. So we follow the steps. The side is. Here we go. The first step is to set. So we are going to choose whichever you want. So you can use M or N. In this case, since we already used M, we try to use N for conveniences. It looks simpler compared to M. So we set N. So N, as you know, is the partial of F with respect to Y. So that is your N, which is, we include the negative sign here. So minus x squared y. We distribute the negative sign, so minus 2x. So this is our starting equation. And cross multiply, so we have df equal to minus x squared y minus 2x times dy. And here, we are going to integrate. So after we have set, and the constant of integration is x. Okay, so now we integrate both sides of the equation. So we have f equal to, so again, x is held constant. So we just copy minus x squared and then integrate y. Will give us y squared over 2. For the second term, you have minus 2x dy. So the variable x is held constant. So we copy minus 2x, integrate dy, we have y. And then we copy the constant of integration represented by phi of x. Okay, so this will be our solution if we can be able to determine the value of phi. So you write first, so minus x squared y squared over 2, and then minus 2xy plus phi of x. Now the next step is to differentiate. So again, the steps set, integrate, and then we differentiate this given function with respect to what? Since we have set n, which is equal to partial of f with respect to y, now we differentiate the function with respect to x. Okay, in this case, y is held constant. So we copy y. So here you copy negative y squared over 2, and then differentiate x squared. We have 2x. In the second term, we have minus 2xy, so we just copy 2y and then differentiate x, and that is 1. And then the third term is a function of x, so differentiate phi of x, it will give us phi prime of x. Now, since the partial of f with respect to x is equal to m, so we equate this to m. So this is our m. Okay, so before we equate, okay, we arrange this first. So minus y squared over 2 times 2x. So we can cancel 2 here. So we have minus xy squared And in the second term, you have minus 2y. This phi prime of x is equivalent to d phi with respect to x. And then the value of our m is, we copy this one, so it's 2x cubed minus xy squared minus 2y plus 3. So at this part of our solution, so we have e equate, we can be able to cancel terms that are not a pure function, okay, or containing variables x and y. So you have minus xy squared, we can cancel this. A pure function of um, y, okay, pure function of y, we can cancel this one. What will remain is a pure function of x, since our constant of integration is a variable x. So we cross multiply, we have d phi equal to, we have 2x cubed plus 3. Okay, we have times dx. And then we integrate. Okay, integrate both sides of the equation. It will give us the value of phi, which is first term, that's 2x to the fourth over 4, our formula. Okay, plus integral of 3 dx, so we have plus 3x. Okay, so this is the value of our phi. We simplify this 1/2, or x raised to 4 over 2 plus 3x. Now we plug in the value of phi to this solution. Now we have, let me erase this part. Okay, so our solution therefore is minus x squared y squared over 2 minus 2xy plus the value of phi, which is x raised to 4 over 2 plus 3x equal to c. So we can arrange our solution. We have over 2, make this negative. Okay, put negative c over 2. Simplify further and then multiply both sides by negative 2, or yeah, negative 2. So we have, okay, so this becomes positive. So you have x squared, y squared. So negative 2 will be canceled. Here we have positive 4xy. Here, this will become negative x raised to 4. And this becomes negative 6x equal to c. Okay, so this is our answer. Now we try to use another method, which is the shortcut. Okay, so we erase now this part of our solution to show you another way of solving an exact DE. Okay, so we integrate m dx. Okay, taking note that y will be held constant. So if we integrate this one, okay, so we just copy 2x raised to 3 minus xy squared minus 2y plus 3 dx. And here, since this is not a pure function of y, you have variable x in each term. That's why you have 0 in this part. So no need to integrate this one because it's not a pure function of y. Again, integrate only those terms that have no x. Okay, so we have 0 here equal to c. So integrate this with respect to x, y will be held constant. It will give us 2x raised to 4 over 4 minus c copy y squared, then integrate x, so y squared, integrate x dx, so x squared over 2. 2y, just copy that, so 2 integral of dx, f xy plus 3x equal to C. Now we simplify. Okay, so this becomes 1/2. Then we can simplify this. We make this C over 2 and multiply both sides by 2. We therefore have x raised to 4 minus, okay, 2 will be cancelled, so x squared, y squared, and then this will become minus 4xy, and then plus 6x equal to C. Okay, so this is now our answer. Okay, so this sign can actually transpose this to the other side of the equation, but they are still the same. Okay, so that's it. That's how you solve an exact equation.